All right, welcome back everyone. In this session, what we're going to talk about is the concept of buckling in columns. And I think it can be best shown with an example. So let's start with an example. All right, so for this example, what we're looking at is this piece of trim right here. So this piece of trim is 5 inches by 1 dimension, an 1/8 inch thick, and it is 3 foot long, right? What I want to know is, if I were to push down on this member, how much force would it take in order for me to cause it to fail, in order to get failure, right? So, as a review, we've talked about this idea of how strong wood is in compression, and that's really what I'm doing, right? I'm putting compression on that member. What we said is to find the compressive strength of any material. We said in compression, we said our stress is equal to the force applied over the area. We may have used F there when I first did it, but I think P and F should be interchangeable. When we talk about buckling, it'll be P, so I'm going to use P over A. When we look at wood in particular, we do know some mechanical properties of wood. We know the modulus elasticity is 2 times 10 to the third KSI, kips per square inch. We know that the maximum tensile stress or compressive stress, or sigma, is 5 KSI. And for this particular one, we know a cross-sectional area, because it's 36 inches long, but our cross-sectional area would be that 5 inches by an 1/8 inch. So with that in mind, I can look at our equation, which says that our compressive stress is equal to our force applied over the area, and plug in what I know. I can have a maximum compressive stress of 5 KSI before the wood fails is equal to this force over the cross-sectional area, which we said was this 1/8 inch times 5 inches. So multiply 5 by 0.125 and another 5, and I get a total force of 3.125 kips. Now remember, a kip is 1,000 pounds, so really what this is saying is I would need to apply a force of 3,125 pounds in order to fail this object, right? Well, clearly that's not the case. I am not that strong to put 1,000 pounds on here while sitting in my office chair. I can see something else is happening before that I get to that value. What is that? It's this idea of buckling. All right, so I put that extra little bit in there, but what happens before we get to that load? It buckles. So with that in mind, we need a new equation to represent how much force I can apply before it buckles. So let's come up with a new equation, which we're going to call the buckling equation. So here I see I have a column that's being pushed with some force P. I'm calling that force PCR, P sub CR, meaning the critical force or critical load. Over a length L, that's the height of our column, and I can see I have that little blue shape would be like my buckling load, right? So to define these variables, our PCR, like I said, is our critical load that leads to this instability. And of course, instability just means that it is buckling. So if I continue to apply that load, it will fail. L is the length of our column. E is our modulus of elasticity. So remember, that's just a material property we can look up in a table. It's based on its stiffness, which we said if we were to look at a stress-strain diagram, it was that slope, right, of the curve. But we're using it a lot in this class, so it's good to know what the modulus elasticity actually means. And then we also have I, and I is our moment of inertia. And we talked about I before, and we said we have one basic equation for I that we're going to use, and we said that was equal to 1/12 the base times the height cubed if we have a rectangle, and I said that would be the only shape we're going to have in this class to make life easier. Of course, we had I-beams, but with I-beams it was basically just a value you're looking up. So 1/12 BH cubed is your formula to find that moment of inertia. So let's get back to our example. In the very beginning of the problem, we were given an E value. We said E was 2 times 10 to the third KSI for wood. We have an overall length. It's 3 feet, which is 36 inches. I think that was given in the original problem, right? Yeah, 36 inches. Then we need to figure out this, this moment of inertia. Now the tricky part about this moment of inertia is, like we said, it's 1/12 bh cubed. What is your base and what is your height? It's all a matter of perspective, right? So if I look at this and I'm looking like in a bird's eye view, meaning this is the plan view, right? Then I have a base of 0.125 and a height of 5. Now the way this works with buckling is our base is the direction it buckles, so it's buckling in that 0.125. If I solve for what that moment of inertia is, I'm going to say this is like condition 1, so I'll say I1 with this 1/12 bh cubed. I end up with like 1.3 inches to the 4th power. Now, if I were to turn it sideways and say, well, what if it buckles in that 5-inch direction, meaning the 5 will be the base, I have a second moment of inertia value, 1/12, the base is 5, the height is 0.125 or an eighth an inch cubed, giving me a value of 0.000813 inches to the 4th. Now, which way is it going to buckle? Well, this should make common sense to you, right? If I were to push down with a force, which direction is it going? Is it going towards the 5-inch or towards the 1/8 inch? Well, it's going in the 5-inch direction, meaning this side's 5 inches. It's going in either this way or that way, right? It would take a lot of extra force to have it come out towards the camera, like this direction if I turn it 90 degrees. So the moment of inertia we want is 0.000813. And what we can say as a general rule for all of these is that the smaller moment of inertia will always govern in these problems. And an easier way to deal with this is when you're doing 1/12 bh cubed, the base is always the larger dimension. So normally if you're doing a problem like this, you don't have to find both moments of inertia. Instead, if it's like, say, a 2x6, then this is 2, this is 6. What is my base? It's the larger dimension. It's 6. So my moment of inertia would be 1/12 6 times 2 cubed. So let's get back to this problem and finally figure out what kind of force I'm actually applying to that wood member. We said that the critical force that would cause instability or buckling is equal to EI times pi squared over L squared. So subbing in my numbers, our E is 2 times 10 to the 3rd kips. We're dealing always in kips and inches, so make sure your units are okay, right? Moment of inertia, we said was that smaller one, 0.000813 inches to the 4th. Pi is pi divided by our length, which is 36 inches, and we are squaring that number. Plugging all in my calculator, I end up with 0.0124 kips. Now remember, kips is 1,000 pounds, so really what I'm saying is 12.4 pounds. Now that seems like a much more reasonable number. I don't consider myself to be a weakling, but I'm sure I can't push down with 3,000 pounds. And if I wanted to, I could definitely break this, you know, just push a little bit more on some unstable and it would probably just break on me, right? So how much force am I pushing? Yeah, I'd say it's probably about 12 pounds. Now if I were to continue pushing with 12 pounds, I'll go, and pretty soon it'll snap. And I suppose you could try that on your own if you really wanted to. So let's take a look at a second example. In this example, what we're going to have is a 10-foot long column here. The dimensions are actual dimensions are 2 inches by 4 inches for a cross section. We're given that it's made out of wood. Our yield stress, or stress, so when it would fail, is 5 kips per square inch. Modulus elasticity is 1.6 times 10 to the 3rd. What we want to find is what's the maximum force I can apply to this 2x4. Well, let's go ahead and start by finding out what is the moment of inertia for this 2x4. So like we just said, it's going to buckle in this direction, right? The bigger dimension. It's stronger the other way, so it buckled in there. So I know that's my base. So for the moment of inertia, it's equal to 1/12 bh cubed. And in this case, the base is that 4 inches. The height is 2 inches. And I know it looks weird to say height is horizontal. If you want to, you can redraw your 2x4 the other way. It doesn't much matter. Plugging that in, I ended up with 2.667 inches to the fourth. All right, and now I can plug it into this P critical equation, which we said was equal to EI pi squared over L squared, where my E is 1.6 times 10 to the third kips per square inch. Our I just found to be 2.667 inches to the fourth. Pi squared over the length of this one is 10 feet. Watch your units. So we want that to be 10 feet times 12 inches per foot, or 120 inches. That's what we're squaring, so our units work out. Plug all that in, and I end up with 2.92 kips. Now, there is one little check we have to make sure of, right? And that is that this is 10 feet, so it's kind of a tall column. If it were shorter, of course, it would take more load. Shorter, shorter, shorter. At some point, it won't buckle, it'll just crush. So that's checking out what we already know. Check the compressive strength of this material and make sure that it's not failing just due to compression, right? So like we just said, compression stress is equal to force over area. I can rearrange this to say that my force is equal to my stress times my area. And we're given in this problem that, that this wood has 5 kips per square inch for a compressive stress. And that's the maximum amount of the compressive stress. For cross-sectional area, it's 2 inches by 4 inches. And that gives me something like 40 kips. So then the question would be, well, what's the answer? Is it 40 kips or is it 2.92 kips? The question would be like, or the answer is found from which would happen first, right? It's always going to be the lower number, but if you think about a column, if I start applying more and more load, once I hit to 2.92, it's failed. So I can't keep putting more and more and more. I can't get up to 3, 4, 5, 6, 7, all the way up to 40. So it's always going to be the smaller number governs if you're checking out to make sure it's going to fail by buckling. All right, so the only other thing that I would mention is that for those who are in a structures type class or have seen this buckling stuff before, the only thing I'm not really accounting for is how these ends are actually attached. This whole thing assumes that it's pinned on both sides, meaning the top and bottom are free to rotate. If I were to clamp it down, you can imagine it would give it much more strength. And I'm not going to get into that in this class, but if you've seen this before or when you move on, it's just another variable you have to add into the equation if it changes. But in here, we'll assume it's always just a pin. And what that means is as I put my force, it's free to rotate either direction. It's not like it's clamped down in a way, right? All right, so I hope you found that helpful, and let me know if you have any questions or comments, and I'll talk to y'all later. Thanks.